Welcome back to the Interview Prep Podcast. Today, we're diving into a topic that comes up in virtually every ML infrastructure interview, designing a real-time ML serving pipeline. We're going to cover feature stores, model serving, and A/B testing, and everything in between. This is where ML engineering meets systems engineering, and it's a critical skill set. Let's start with what we mean by real-time ML serving. We're talking about systems that take a request, compute features, run inference on one or more models, and return a prediction, all within a tight latency budget. Think recommendation systems, fraud detection, dynamic pricing, or content ranking. These systems serve millions of requests per day with P99 latency requirements often under 50 to 100 milliseconds. First, the requirements. When you're whiteboarding this system, clarify these dimensions. What's the latency budget? Real-time usually means under 100 milliseconds end-to-end, but some use cases need single-digit milliseconds. What's the throughput? Are we serving hundreds or millions of requests per second? What's the model complexity? A simple logistic regression serves very differently from a large neural network. How often do models update? Daily retraining, hourly, or continuous? And what's the feature freshness requirement? Do you need features computed in the last second, or are daily aggregates sufficient? Now let's build the architecture from the ground up. The request flow looks like this. A client sends a prediction request, which hits an API gateway, then flows to a feature service that assembles all needed features, then to a model serving layer that runs inference, and finally returns the prediction. Let's break down each component, starting with the feature store, which is often the most complex and most important part. A feature store is a centralized system for storing, serving, and managing ML features. It solves a critical problem in ML, the training serving skew. If you compute features differently during training versus serving, your model will behave unpredictably in production. A feature store has two main components. The offline store handles batch features for training. This is typically backed by a data warehouse like BigQuery, Snowflake, or a data lake on S3 with Parquet files. Features are computed by batch pipelines, often using Spark or SQL, and stored with timestamps for point-in-time correctness. The online store serves features in real time for inference. This is backed by a low-latency key-value store like Redis, DynamoDB, or Cassandra. Features are pre-computed and cached here, typically keyed by entity ID like user ID or item ID. Retrieval latency should be single-digit milliseconds. The key technologies here are Feast, which is the most popular open-source feature store, Tekton for managed solutions, and Hopsworks. For the interview, know that Feast provides a Python SDK for defining features, materialization jobs to sync offline to online stores, and a serving API for real-time retrieval. Now let's talk about feature types. You have batch features that are pre-computed on a schedule, like a user's average purchase amount over the last 30 days. You have streaming features that are computed from real-time event streams, like a user's number of page views in the last 5 minutes. And you have on-demand features that are computed at request time from the request payload itself, like the time of day or the specific item being viewed. Streaming features are where things get interesting. You need a stream processing engine like Apache Flink, Kafka Streams, or Spark Structured Streaming to consume events from Kafka, compute aggregations in real time, and write results to the online store. This is critical for use cases like fraud detection, where you need to know a user's transaction velocity in the last minute. Moving to model serving. This is the component that loads a trained model and runs inference on incoming requests. There are several approaches. First, you can serve models behind a REST or gRPC API using frameworks like TensorFlow Serving, Triton Inference Server, Torch Serve, or lighter-weight options like Fast API with Unicorn for simpler models. Triton Inference Server from NVIDIA is the gold standard for GPU-based serving. It supports multiple frameworks including TensorFlow, PyTorch, ONNX, and TensorRT. It provides dynamic batching, which collects multiple requests and processes them as a batch to maximize GPU utilization. It supports model ensembles, where you chain multiple models together, and concurrent model execution across multiple GPUs. For CPU-based serving of simpler models, ONNX runtime is excellent. You can convert models from any framework to ONNX format and serve them with optimized CPU inference. This is often the right choice for tree-based models like XGBoost or LightGBM. Let's talk about model optimization for serving. Quantization reduces model precision from 32-bit floating point to 16-bit or even 8-bit integers, cutting memory usage and improving throughput with minimal accuracy loss. Pruning removes unnecessary weights from neural networks. Knowledge distillation trains a smaller student model to mimic a larger teacher model. And TensorRT compilation optimizes neural network graphs for specific GPU hardware. These techniques can improve serving latency by 2 to 10 times. Now for the model registry and deployment pipeline. You need a system to version, store, and deploy models. MLflow is the industry standard model registry. It tracks model versions, metadata, metrics, and artifacts. A typical deployment pipeline looks like this. A training job produces a model artifact, registers it in MLflow, triggers a CI/CD pipeline that runs validation tests, packages the model into a container, and deploys it to the serving infrastructure. Let's get into A/B testing, which is crucial for any ML-powered product. A/B testing for ML models is more nuanced than simple web A/B testing. You need to route a percentage of traffic to the new model while the rest goes to the current production model. Then you compare business metrics, not just model metrics, to decide whether to promote the new model. The traffic routing layer sits in front of your model servers and directs requests based on experiment configuration. This can be implemented with a service mesh like Istio, a feature flagging system like LaunchDarkly, or a custom routing layer. The key requirements are deterministic assignment, so the same user always sees the same model variant, configurable traffic splits, and the ability to quickly roll back if something goes wrong. Beyond simple A/B tests, there are more sophisticated approaches. Multi-armed bandits dynamically allocate more traffic to better performing variants, reducing the cost of exploration. Interleaving is used in ranking systems where you interleave results from two models and measure which results users prefer. Shadow mode runs the new model alongside production without serving its results, letting you compare outputs and catch errors before they reach users. Statistical rigor matters. You need to define your primary metric, calculate the required sample size for statistical significance, run the test long enough to account for day-of-week effects, and use proper statistical tests. Common pitfalls include peaking at results too early, not accounting for multiple comparisons, and ignoring novelty effects. Let's discuss the monitoring and observability layer. ML systems can fail silently. The model keeps returning predictions, but they're wrong. You need to monitor several things. Data drift detection checks whether the input feature distributions have shifted from what the model was trained on. Model performance monitoring tracks prediction quality metrics in real time, which requires delayed ground truth labels for some use cases. Infrastructure metrics like latency, throughput, error rates, and GPU utilization are standard. And prediction distribution monitoring watches for unexpected shifts in the output distribution. Tools for this include Evidently AI for drift detection, Prometheus and Grafana for infrastructure metrics, and Custom Dashboard for business metrics. Set up alerts for anomalies in any of these dimensions. Now, for some advanced topics. First, multi-model architectures. Many production systems use multiple models in sequence or parallel. A recommendation system might use a retrieval model to generate candidates from millions of items, a ranking model to score and order those candidates, and a re-ranking model that applies business rules and diversity constraints. Each model has different latency and throughput characteristics and may need different serving infrastructure. Second, caching strategies. Model predictions can often be cached, especially for items or entities that are requested frequently. A two-level cache with an in-memory cache like Memcached for hot items and a distributed cache like Redis for warm items can dramatically reduce compute costs and latency. Cache invalidation happens when model versions change or when input features update. Third, autoscaling. ML serving workloads are often bursty. You need horizontal pod autoscaling based on GPU utilization, request queue depth, or custom metrics. Kubernetes with GPU support and tools like Kata for event-driven autoscaling are the standard approach. Pre-warming is important for GPU-based models because loading a model onto a GPU takes time, so you want spare capacity ready. Fourth, consider the cold start problem. When a new model version deploys, the first few requests may be slow as the model loads into memory or compiles for the specific hardware. Solutions include pre-warming new pods before routing traffic to them, blue-green deployments where the new version is fully ready before switching, and canary deployments where you gradually shift traffic. Here's your whiteboard summary. Draw the flow from left to right.